Good morning. So today we will learn resolution of vectors, how to resolve one vector to other vectors, two or more vectors. And we will also see why it is easier to pull something than to push. And also we will see why it is easier to pull if the rope is longer than if the rope is shorter. So these are the things which we are going to learn today. Now what is meant by resolution of a vector? What is meant by resolution of a vector? In the last class, we saw the addition of vectors. We saw that you can you can add two vectors and you will get a new vector. So we can divide any vector to two vectors as well, which means we can express any vector as the sum of two vectors. That is called resolution of vectors. So resolution of vectors means representing a vector as the sum of other two vectors. So let us consider a vector A. Now, if I want to express this vector A as the sum of two vectors, in the first case, I will consider that the two vectors will be perpendicular to each other. So, I am going to resolve this vector A in two directions. Okay. We know that the horizontal direction is usually called the x direction and the vertical direction is usually called the y direction. So if I'm resolving this into two vectors which are perpendicular to each other, which means the angle between these two vectors are 90 degrees, we can call them as the components of vector A. So if this forms a vector x, and if this forms a vector y, and if the angle between vector A and one of the vectors is alpha, then I can express vector A as equal to vector x plus vector y. This is what we call that vector A is resolved into two perpendicular directions. Here one vector is represented as the sum of other two vectors which are perpendicular to each other. Now let us see what will be the magnitude of x and what will be the magnitude of y in terms of the magnitude of vector A and the angle alpha. For that, let me note these points as O. This is A, so we use that letter. Let me put this as B, this as C, and this as D. Now from here, consider the triangle OBC. OBC. These are perpendicular. So this angle is 90 degree and triangle OBC is a right angle triangle. So from triangle OBC, I can say that OC is x, right? I can say that cos alpha is equal to adjacent side by hypotenuse. The adjacent side here is OC divided by hypotenuse is OB, right? So this is equal to OC, as you can see here, is x. So x divided by OB, you can see has magnitude A. So x by A, or the component x is equal to A times cos alpha. So this is how you can represent the horizontal component or the component in the x direction. Component in x direction is equal to A cos alpha, where A is the magnitude and alpha is the angle with the x-axis. Now let us consider the other component. For that, let me consider sine alpha. Sine alpha means from the same triangle, it is opposite side by hypotenuse. Opposite side is BC, right? So BC divided by hypotenuse is OB. But we know that BC is equal to OD, which is 1. So I can represent this as equal to y divided by OB, as you can see is A. So y by A or y is equal to A sine alpha. So we got both the components x and y. So whenever we are okay. So whenever we are resolving a vector into two perpendicular directions, then the two components will have magnitude given by x is equal to a cos alpha and y is equal to a sin alpha. So this is how we can resolve a vector into two perpendicular components. Is that clear to you? Is this clear to you?
Yeah, teacher.
Okay. Now, suppose you are resolving vector A into two components between which the angle is not 90 degree. That means you will come across situations where you have to resolve a vector in two directions, but the angle between those two directions may not be 90 degree. In such case, what will be the two components? That's what we are going to see. We will not be deriving the expression. We will just write the expression and we will see how that expression turns into this. So here we are trying to resolve any vector, suppose A, or here we used A. I'll mention this as R. And we are resolving into one in vector X and another one may be this one, vector Y. So this is one vector and let me put this as another vector. Another vector Y. So we are resolving now this vector R into X and Y, but you can see here the angle between X and Y are not 90 degree. So that is, you are resolving one vector into any two directions, any two vectors. Suppose this angle, the angle made by this vector which we are going to resolve, with one of them is alpha and with another one is beta. See, you are resolving a vector into any two directions, not perpendicular directions. Then I'm going to just write the equation. One of those component x is given by r, I'm taking the other angle, sine beta divided by sine alpha plus beta. And the other component y is equal to r sine alpha divided by sine alpha plus beta. Okay, we are not going to derive these expressions, but remember when I am taking the x component, I use the other angle, sine beta in the numerator. Similarly, when I am writing the other component y, I use sine alpha, the other angle. Okay, you have to note this down. And let me show you how this will turn to these equations if alpha plus beta is 90 degree. Alpha plus beta is 90 degree means the angle between the two components are 90 degree. Then these equations will become this. Let us see how it is. So if these two are perpendicular to each other, this equations should come out as this, right? So we will put the condition that alpha plus beta is equal to 90 degree if. Okay. Then what will be beta? Beta will be equal to 90 minus alpha, right? So what is sine 90 minus alpha? Instead of here, what is sine 90 minus alpha? That is equal to cos alpha. And what is sine alpha plus beta? Alpha plus beta is 90 degrees. So sine 90 is 1, right? Now, if you consider these two expressions, let us see what x will become. X will become equal to r. Instead of sine beta, that is sine 90 and minus alpha, you have cos alpha. R cos alpha divided by sine alpha plus beta, that is sine 90 is 1 by 1. Or y is equal to r sine alpha divided by sine alpha plus beta is 1. See? it turns into this equation. Did you get it? This is how we see whether these two equations which we wrote will be correct. So whenever the angle between the two components are any angle, you can use these two equations, and if you are resolving them into two perpendicular components, you can use this equation. Is this clear to you? Is this clear to you?
Yes.
Okay, so that's all I wanted to say about the resolution of vectors. You need to memorize this equation and this equation, and you have to understand the situation in which we are representing them in the component form. So you can resolve a vector into two perpendicular components or to any two components, which may or may not be perpendicular to each other. Now, let me consider the case when you are pushing or pulling something. When you push or pull something, what is happening? You are applying force, right? Now, if I want to move something, I have to apply force. How can I apply force? I can either push it or pull it. Now let us see which one will be easier. I'll write the answer straight away and explain why pulling is easy. So my question here is why pulling is easier than pushing. Do you agree to this? Have you experienced and do you agree to this?
Yes,
Pulling.
teacher.
No, Irfan, you don't agree?
No,
Pulling.
teacher, I agree. I said yes, I agree.
Yeah, I have a chair here, right? So I'm going to push it, okay, and pull it. So pulling is easier, but this is not too heavy and there are wheels below, so it's not that hard. But if you want to push a trolley which is heavy with a lot of things, then to push it or pull it, try both. Pulling will be easier than pushing. Let us see the explanation in terms of physics, how we can show that pulling is easier than pushing. Now, when you are pushing or pulling something, it's easier to move a light object than a heavy object, right? It's always easier to push or pull a light object than a heavy object. Why? More the weight of the body, more will be the difficulty. Why? If you are moving something, there is something called friction that prevents motion. More friction means more difficult to move. Okay. Now, if the body is very heavy, there is more friction. So, as the weight of an object is more, friction will be more. And it will be hard to move. This is the case. That is why we can easily move a light object, but it's very hard to move a heavy object. If there is more weight, what happens? There will be more friction between the body and the surface on which it is moving, and therefore it will be hard to move. Now, if it is light, friction will be less and we can easily move. That's why in order to reduce friction, sometimes we use wheels below heavy objects, or sometimes we move it on a smooth platform. It's easier to move objects on a smooth platform than a rough platform because the friction is less. So our idea is to reduce friction so that it will be easier to move an object. Now, let us consider a road roller. What is a road roller? Have you seen a road roller?
Yes, teacher. In
Where?
Bangladesh.
In road
No, no,
construction.
it is used to construct the road.
Yes. It's used to construct roads. So when there are road construction, they use road rollers. Okay, and these road rollers will be rolled on the surface, rough surface, before the tar is properly placed. And then, suppose you are trying to, there is no space, I will draw it a little bit down. So here I have a road roller here. Now suppose there is a handle here and I am going to push this. Suppose I am going to push. So I'll be applying force in this direction, F. And this force is resolved into two directions, horizontal and vertical. So if I resolve this force in two direction, the horizontal component Fx, which helps in moving in the horizontal direction, and the vertical component is Fy, which is downwards. And we know that the weight of this object is acting downwards as well. So a part of the force we apply while pushing. So this is pushing. When we push, a part of the force that we apply is resolved in the downward direction. Only a part will be available in the horizontal direction. So both the weight and this force is in the downward direction. So when we push it and try to move it, what happens? The apparent weight means the felt weight is equal to W plus Fy, because both Fy and W are in the same direction. So when you are adding two vectors which are in the same direction, you have to add them. They are in the same direction. So the apparent weight is W plus Fy, which means the weight is more. So when the weight is more, what happens? Friction is more. And it is hard to move. Did you get it? When you push something, a part of the applied force adds to its weight. So there was more weight than its actual weight, and the friction will be more, and therefore it is hard to move. Now at the same time, suppose I am trying to pull this. So when I pull, I'll be applying force in that direction, right? So this is a pull, and I can resolve this force into the horizontal component and the vertical component. Horizontal component Fx will help me in moving the object in the horizontal direction, and the vertical component Fy will lift it. It's in a direction opposite to that of the weight. So what about during pull, the apparent weight? During pull, the apparent weight is equal to W minus Fy. It's minus because W and Fy are in opposite direction. So the apparent weight is less than the actual weight, which means the weight is reduced. So what happens? Friction is reduced. And therefore, it is easy to pull. This is why we can say that it is easy to pull something than to push. Is this clear to you? Is this reasoning clear to you?
Yes, teacher.
Okay.
Yes, teacher.
It is easier to pull something than to push a weight. Now, if we want to move it. Now, let us see why while pulling, we have to use a longer rope than a shorter rope. I will tell you one example. Have you seen a trolley? What can I tell? Book bags, school bags. School bags, which are trolley bags. Have you seen that? Usually, the children of primary school, they have a lot of books. Some schools don't allow to keep the books at school. They have to carry it home and bring it back almost every school day. So have you tried to weigh their bags? They are very heavy. The weight of the bags are too heavy. That is an important issue. So they have trolley bags. And have you seen the handle of the trolley bags? When they are keeping it or somewhere, they will reduce the length of that handle. But when they are pulling it, what happens? They will increase the length of the handle. Why they are increasing the length of the handle? It's because it's easier to pull with the longer handle than a shorter handle. Now we will see how, using physics, the idea of vectors and resolution of vectors, we can explain this. Okay, so have you used trolley bag yourselves? Have you used it?
Yes, teacher.
And do you elongate the handle while moving it? Irfan?
Yes, yeah.
Have you
So I think because the
Yes?
more the vertical component, I think the less effort, right?
Yeah, the vertical component. Yeah, the vertical component is.
The more the vertical component, the effort is less. I think for this one.
Okay, okay. Let us see how you can show that mathematically. While pulling with a longer rope, or I'm going to take the case of boat first. That's why I'm using longer rope. Why pulling with longer rope is easier than while using a shorter. Let me take the case of a boat which is in water. You have boat in water and this is the shore. You have a shore here and someone is trying to pull that to the shore. Okay, so this is the direction in which force is applied. So when you apply force in this direction, it can be resolved in the horizontal direction that will help to move towards the shore, Fx. And here you have, the idea is to get it here. And there will be a vertical component, Fy. Now, this board is in water. So, Fy, the vertical component of force, will help to lift the boat from water. It will act along with the upthrust and this force will lift the boat from water. And the horizontal force is that which will help the boat to come to the shore. Suppose this angle is theta. Okay, you remember how we resolve one force in the horizontal and vertical direction, how we resolve a vector. So when we resolve a vector, what will be the horizontal component? Fx is equal to, Fx is equal to, this angle is theta. So horizontal component and vertical component. Fx is equal to F cos theta. Just now we saw the x component is cos theta, the y component is sin theta. So fx is equal to f cos theta, okay, and fy is equal to f sin theta. We just saw that that's how we can resolve a vector into two perpendicular directions. Now, this is theta, right? Now, what about theta, value of cos theta? What is cos 0? 1. What is cos 90? Is equal to 0, right? Cos 90 is 0, cos t is 0 is 1. Now, use depending upon the length of the rope, the theta can be different. Suppose I'm using a longer rope, then the theta will be lesser, right? Angle will become lesser. As the angle becomes lesser, cos theta will be more. See here, theta can go from 0 to 90 degree. Lesser the value of theta, more will be the value of cos theta, or more will be the horizontal component. So if you are using a longer rope, theta will become smaller and therefore the horizontal component of the force will be more. Is that clear to you? Is that clear to you?
Yes, teacher.
Yeah,
Yeah.
teacher.
Okay. Now, as we told the case of that school bag, trolley bag. So when you consider that trolley bag here, suppose this is the trolley bag and there is a boy who pulls it with the handle. The handle is here. So the boy is standing here. This is the height of the boy. Okay. And this is the trolley and he is pulling this with the handle. This is the angle theta. Now, if he is not elongating the handle, then from the same height, let me consider the same height and this is the trolley. So here will be the trolley bag because this is the height. So the trolley bag is here. They did not elongate. So what about this angle? This angle is more than this. If this is theta 1, this is theta 2, you can see that theta 2 is more than theta 1. So our idea is to reduce theta so that the cos component will be, the horizontal component will be more, and that will reduce that will ease, that will provide more horizontal component of force and help to move the trolley forward. So that is why we always say that by pulling with longer rope or longer handle is easier than pulling with a shorter handle. The shorter handle will make the angle between the applied force and the body less. So the cos component will be more, or the horizontal component of the force which helps in movement will be more. So that is what I would like to tell you about why pulling with longer rope is easier. So we told that we can resolve a vector into two components. So when we resolve the vector into x and y components, there is an easier way in which we can represent a vector, which is called the coordinate form of vectors or the component form of vectors. Component form of vectors. So suppose you have a vector A which is resolved into along the x-axis and y-axis. Okay, so suppose this distance is ax, and this distance is ay. When we learned unit vectors, I told you there is a notation for the unit vector along the x, y, and z direction. What is the notation for unit vector along the x direction? What is the notation for unit vector along the x direction?
I.
I. So along the x direction, you can represent the unit vector with I cap. Along y direction,
J.
j cap. So you can represent the magnitude ax and unit vector I as the component along the x direction, and the magnitude ay and unit vector j as the component along the y direction. So vector A can be expressed as axi plus ayj. This is the component of vectors in two dimensions. Okay, suppose I have a position vector here, object is here at this place. So I will require x direction, y direction, and z direction to represent that vector, right? So how will we represent in the component form, that is in 3 dimensions? So let me consider a vector P. Okay, I have a vector P, so I can represent this is x direction, this is y direction, and this is z direction. So first let me put it down to the xz plane. Okay, so parallel to this I am drawing here. So I have here Py. Suppose Py is the coordinate along the magnitude along the y direction. and this is here. So I am going to draw parallel to this line. I will get here Px. Px is the magnitude of this vector P along the x direction. I am going to draw parallel to the x-axis here. So I have here Pz. So we know that along the x direction, the vector is a unit vector is I, along the y direction it is j, and along the z direction it is k. So I can represent this vector p in 3-dimension coordinate form. P is equal to pxi plus pyj plus pzk. This is how I can represent or resolve a vector in 3 dimensions. This is how I can resolve a vector in 2 dimensions. And this is how I can resolve a vector in 3 dimensions which are perpendicular to each other. Now, if I resolve this vector in 2 dimensions, I can get the magnitude of this vector as equal to root over ax square plus ay square. And if I want to write the unit vector in that direction, I can write it as vector A divided by its magnitude. So unit vector along this direction is represented as vector A is axi plus ayj divided by root over, because magnitude is ax square plus ay square. Similarly, can you tell me how can I represent the magnitude of this vector p? How can we represent the magnitude of vector p? How will I represent the magnitude of this vector p? Root over, what are the components? Pxi, pyj and pzk, right? So I can write it as px square plus py square plus pz square. This is the magnitude of the vector, and I can represent the unit vector in that direction as equal to pxi plus pyj plus pzk divided by root over px square plus py square plus pz square. Is it clear to you?
Yeah, teacher,
Okay.
time finished.
Time finish. So next class I will show you with actual examples with numbers how we can represent the magnitude, direction, how we can add, subtract and all using the component form.